Our first presenter is Dr. Jose Alvarado. He is a technical advisor for AFOTEC Det 5 at Edwards Air Force Base. With over 33 years of developmental and operational test and evaluation experience. He is interested in applying model-based systems engineering concepts to the flight test engineering domain and implementing test process improvements through model-based testing. Jose holds a bachelor's in electrical engineering from Cal State University, Fresno, an MS in electrical engineering, and a bunch of other degrees, like the rest of us. He serves as a technical or adjunct facility member for the Math and Science and Engineering Department and a technical career education department at Antelope Valley College. He is also a member of ITEA, the International Test and Evaluation Association. Welcome, Dr. Alvarado.
Thank you. Well, thank you very much for being here. Hopefully my presentation won't be too distracting with my camera being off and me being doing this from remotely as we start. Most of the time when I end up starting a presentation, I like to start off with definitions. And the first definition that I like to start off with is the definition of digital engineering. And digital engineering, as we all know, is defined by the DoD, is an integrated model-based approach that uses authoritative sources as system data and models across disciplines to support all phases of a system's lifecycle. This approach connects processes, data, and capabilities to enhance transparency, increase confidence in system performance throughout its particular lifecycle. However, this particular knowledge gap within the T&E community regarding these particular applications is kind of lacking as far as there's not a lot of use in it and people still don't know what to do. This particular presentation explores how flight test operations can use MBSE and align them with our budding AFOTEC's digital strategy that we're currently working on. And by adapting these practices, operational testing of new weapon systems can become more efficient and more effective. The current flight test planning process uses a highly detailed document-intensive process to maintain consistency between critical documents and the evolving system under test, or what I'll call an SUT, which requires stringent and ongoing configuration management. By integrating flight test planning into a model-based testing framework, or an MBT framework, implemented with an MBSE structure environment, we can better manage this particular complexity of this document-centric approach. This presentation basically builds on two ITEA publications that extends the established model-based gray box testing techniques that I developed and created during my dissertation. And I'll introduce a tailored MBT methodology specifically designed for flight test applications. To validate this proposed MBT process, a baseline test case was created using SysML, using the Cameo Systems Modeler software within an MBSE framework. I used a fictitious CSARL system, which stands for the Search and Rescue Locator is what we end up doing, called, and it's designed as a portable handheld GPS receiver for aircrew and rescue teams, and is modeled by using system descriptions and the initial capabilities document that we use to train all brand new AFOTEC employees that come into our organization. When I ended up using these documents, I ended up creating the particular system model since no model was created. And then once I was done with that part, I ended up using the AFOTEC test planning guide, and I ended up creating the model or the approach that you end up having on the AFOTEC side of the fence. So basically, the model that I have now serves as a comprehensive benchmark for comparing both the traditional document-based methods with model-centric processes using this gray box inspired technique within an MBSE environment. Now, the AFOTEC methodology is represented by a series of diagrams that define the test planning process for the CSARL system. This structured approach begins with the identification of critical operation issues, or what we call COIs, which are the key questions that are developed by test team members to determine whether the SUT can effectively perform its intended mission within the expected operational environment. Once defined, these particular COIs are further decomposed into what we call measures of effectiveness, which provide a more detailed assessment of the SUT's capability to achieve its mission objectives and deliver the desired outcomes. This hierarchical breakdown ensures that the test planning process remains focused, traceable, and is mission relevant throughout the process. Now, each one of these MOEs is further refined into what we call measures of performance, or MOPs, and measures of suitabilities, or MOSs. These metrics provide a more granular evaluation of the SUT, focusing on both its operational capabilities and its abilities to support and be sustained within the intended environment. MOPs assess how well the system performs specific functions, while MOSs evaluate whether the system is reliable, maintainable, and logically supported under realistic operating conditions. Oops, one too many here. Here we go. That's where I was at. Here we go. So now, to further evaluate this particular process, once I established a baseline, I ended up creating another case study to kind of start comparing the process and to see how I can use this process as we go along. So in order to evaluate and validate this new AFOTEC methodology that I ended up creating, I ended up putting it into the second test case, again using Cameo. This particular new case study kind of had a balance between complexity and manageability. The second case study that I ended up using was based on a fictional airborne ISR platform referred to as the EX Airborne Platform, which is featured in the Effective Modeling Based Systems Engineering textbook as an example for developing various SysML diagrams used to define complex systems. The EX platform is a multi-sensor airborne system designed to conduct intelligence, surveillance, and reconnaissance missions, and it collaborates with ground stations and partner organizations to collect, process, and disseminate ISR products while performing aerial imaging and sensing operations to support those particular mission objectives. So as we can see, this particular system is getting a little bit more complex, and more things are involved within this particular process that is developing this particular system. Now, since both of these particular systems are fictitious and ended up putting them together, we went through and created the COIs for this particular EX platform. What we ended up doing is I took the AFOTEC methodology that I developed for the CSARL system, and I ended up reusing it as the foundation for this particular second test case, and I adopted the needed and redefined the COEs for this particular platform. I leveraged the flexibility of SysML and its reusability features where I systematically decomposed all of those new COIs into new MOEs using the CSARL ones as model templates. This particular approach streamlined the development process, and it demonstrated how the model reuse can enhance consistency and efficiency across different test case applications within an MBSE framework. Now, once again, the flexibility and the reusability of these particular models ended up allowing me to take the MOEs and then break them down into the individual MOPs that we end up having. What you end up seeing is the next set of slides are all of these particular MOEs that get broken down into all of the individual MOPs as they go along. And as you can see, because of the EX platform being a little bit more complex, we end up seeing more COIs, more MOEs, and more MOPs and MOSs as we go along. So like I said, the increase of these enabled me to create more comprehensive definitions of the system and its expected capabilities and supportability requirements that the system required. Now, this particular scaling effect illustrates how the MBSE and the MBT framework effectively accommodates increasing system complexity while still maintaining clarity, traceability, and structured test planning throughout the modeling process. Now, a third case study features a model that was developed by the Air Force Material Command, the Digital Engineering Program Office, known as the Next Generation Sensor System. This particular model serves as an instructional tool for both government and contractor personnel, demonstrating how to implement the weapons GRA structure in practice, and how we can end up using it to develop models that are coming into the new acquisition process. The NGS system represents a notional airborne sensor platform designed to support the ISR mission by integrating various sensor configurations. So this particular case study is very similar to the EX platform that was highlighted in the textbook. This one is also a little bit more of a complex system where it provides a practical example. And again, applying my gray box expired testing techniques with an MBSE framework, I ended up utilizing the SysML diagrams and was able to create the system behavior and the structure models along with these particular ones, and apply the AFOTEC methodology across the range of these systems complexities. Now, the reusability feature of the SysML and the Cameo software effectively leveraged and streamlined this particular model development when I ended up applying it to the NGS system. And it actually became a little bit easier because the airborne system, or the EX airborne sensor platform, is very, very similar to the NGS system. So therefore, a lot of it ended up being ported over. So because the systems were very, very similar, the COIs all remained the same. The MOPs and the MOEs, MOPs, and MOSs were functionally identical. The only difference between them was just basically the naming nomenclature, changing it from basically an EX sensor platform labeling to the NGS process. So again, this particular system also reinforces the concept of reusability, going from one model to another model, and the expansion of how the ease of use when you end up going from models that are very, very similar with each other. It's really just a cut and paste type of a process. Now, these particular summary tables provide a clear comparison of the key features across the 3 test case models and visually demonstrates this progressive increase in system complexity. The number of SysML elements in the diagrams increase with each successive case study, reflecting the transition from a simple baseline system in the CSARL test case to the more complex real-world scenario of the NGS system. This upward trend underscores the correlation between system complexity and the modeling effort required, and highlighting how these intricate systems demand greater detail and more extensive diagramming to capture their full system behavior and their structure. The selection of the CSARL based test case, followed by the EX platform and the NGS system, was very, very deliberate. And the reason they were deliberate was because they ended up showing this progression from something similar to a little bit more complex to an actual simplified real-world example. So when I went to apply this particular research, I ended up evaluating the adaptability of the AFOTEC's methodology process, which is our test planning process, within an MBSE based MBT approach across a range of applications, from systems with distinct mission sets to those with similar operational goals, but varying the levels of its particular complexity. This comparative analysis, again, reinforced the methodology's flexibility, scalability in supporting model-centric test planning for diverse systems and their different types that we have. Now, as an MBC adoption grows in the DOC aerospace sectors, there's an increased need for clear definition and a structured ontology for SysML model reuse. Drawing from software engineering, where reuse often involves the adapting of the existing artifacts via a copy and paste method, this particular concept extends functionality and supports integration into new systems. Literature constantly cites model reuse as one of the major advantages of MBSE-based model-based developmental testing over traditional document-driven approaches. So now, using AFOTEC's continuing test mission, reuse enhances the efficiency and the effectiveness by enabling information sharing, automated tasks, and supporting standardization and repeatability. So as a standard metric used to measure system software reuse is what they use is called the product reuse percent, or the PRP. This particular metric indicates how much of a product can be attributed to reuse and is calculated using the amount of reused source instructions, or RSI, and the shipped source instructions, SSI. When the product has no reuse instruction, RSI is equal to 0, resulting in a PRP of 0. When RSI is equal to ISI, all shipped instructions result from reuse, and thus PRP is equal to 1. So PRP lives between 0 and 100%. Another metric that is used by software is in reuse is the reuse value added metric, or the RVA. This particular metric evaluates the potential benefits of consuming and producing reusable software, and is based on the productivity index that determines the effectiveness of reuse across multiple products. Products that do not reuse code have an RVA of 1, while an RVA of 2 indicates that the product is twice as effective than if the product was created without reuse. So the total effectiveness of the product developed is higher when the RVA score is higher. So since these particular models consist of modeling elements rather than lines of code, we redefine the traditional reuse metrics to better align with the MBSE environment. Specifically, we redefine RSI as reused elements, or what we call RSE, and SSI as model elements, or ME. This allows us to introduce a new MBSE appropriate metric called the model reuse percent, or MR%, which is analogous to the traditional PRP, which is calculated using these updated terms. Because these reuse elements in our models serve as the same purpose as the reused lines of code in our software, and the number of test products correspond to the number of models, we can also restate the RVA formula accordingly, in where we can rearrange the particular numbers to suit our new definitions that we end up having. This redefinition allows us to apply familiar reuse metrics in the model-based context and provides a more accurate and meaningful assessment of model reusability and efficiency in the AFOTEC MBSE framework. Now, this particular figure illustrates the comparison between the MR% and the RVA metrics across the 3 test models that were developed in this particular study. We see that the RM% is primarily used to evaluate direct reuse of artifacts between 2 consecutive generations of models, offering a straightforward measure of how much content from one model is carried over to the next model. In contrast, the RVA metric provides a broader perspective, capable of assessing reuse not only between consecutive models, but also between the baseline model and the more advanced multi-generational models. By applying both metrics, we can gain a comprehensive understanding of the extent of and efficiency of model reuse within the MBSE-enabled MBT process. These metrics offer a valuable insight into how reusable content evolves over time and how test planning models can become increasingly effective through strategic reuse and adaptation. This particular chart illustrates the calculated metrics used to assess reuse between the CSARL model and the EX platform models, specifically focusing on the RM% and the RVA. The average RM% between the 2 models was determined to be 25.5%, indicating that approximately 1/4 of the CSARL model artifacts were successfully reused in developing the EX model, despite the differences in the system and the complexity and the mission scope. This demonstrates that even when the systems are not identical, meaningful reuse of MBSE artifacts is still achievable. Additionally, the RVA for this comparison was calculated at 1.72, meaning that the EX test planning model was 72% more effective in produce as a product than it had if it had been created entirely from scratch. Now, similarly, this particular table highlights the percentage of element reuse between the EX platform and the NGS system model. Now, the RM% between these 2 models averaged 100%, which is what we would expect because the EX test case is completely reused in developing the NGS model test case, as I explained earlier. This high level of reuse is expected because given that both systems are ISR platforms with highly similar mission sets and structural elements. More significantly, the RVA metrics between the EX and the NGS model averaged 2.0, indicating that the test planning model was twice as effective compared to building it from scratch. Additionally, despite the generational and architectural differences between the NGS and the baseline CSARL system, the RVA metrics between the 2 of them averaged at 2.08, demonstrating that even across distinct systems, the reuse of test planning elements still provides more than double the efficiency coming from one generation to two generations being removed. These particular metrics, again, emphasize the power of reuse within an MBSE-enabled MBT process, reinforcing that value of enhancing productivity and reducing development efforts across different but related system models. Now, these particular test case models demonstrate that the MBSE process is effective across a range of system complexities from simple to highly complex artifacts. Notably, the results show that even when working with projects that share low similarity, adopting the AFOTEC MBT methodology was more feasible than initially anticipated. These findings underscore that the value of both incremental MBSE adoption and model-driven test design is something useful. Furthermore, the study reveals that even basic MBSE efforts contribute meaningfully to the process of understanding and support of the creation of well-documented, reusable model libraries. A 25.5% reuse rate across the different modeling domains signals strong potential for scalability and efficiency. Importantly, these particular models develop a thorough reuse, provided significantly more efficiency than those built from scratch, affirming the benefits of the this reuse-centric approach. These particular insights not only validate the AFOTEC's methodology's applicability, but also establishes a solid foundation for advancing effective, standardized, and model-driven test development within the DoD testing enterprise. So in conclusion, the integration of MBT within an MBSE framework offers significant advantages to further test planning efforts. One of the most impactful benefits is the ability to derive and reuse test models and plans, which substantially reduce the time and the resources required to test new SUTs, which is a key objective of the DoD's Digital Transformation Initiative. Although the degree of reuse is influenced by the differences between individual system models, many critical components can be effectively duplicated and tailored to meet these evolving system requirements. By implementing the AFOTEC test methodology through a model-based approach, organizations can take full advantage of MBSE artifacts to enhance flight test planning and documentation. This particular strategy not only promotes reuse, but it also strengthens configuration management, consistency, and standardization across the DoD testing enterprise, laying the groundwork for more agile and efficient future testing within the operational testing environment. So that is a quick little rundown of the stuff that I've been working on. Is there any particular questions that I can hopefully try to answer?
We do have about 5 minutes for questions before we need to get going on the next talk. So you're welcome to, I can either run the mic to you, you can use the microphone over there. Thank you so much, Dr. Alvarado.
Thank you. Alrighty, I'm gonna go ahead and stop sharing my screen there and get you ready for the next one. So I will go ahead and mute myself.
I'll start. I have a question. If nobody else does.
Okay.
So I love the idea that model-based testing and model-based sensitive engineering could promote repeatably testable MOPS, MOs, MOSs across systems or across versions of systems. I was wondering if you've done any thinking about how to perchance promote making sure that those initial models are of high quality when it comes to MOPS, MOs, especially when things like humans and human requirements are involved, so that we're not passing forward less than optimal requirements and test requirements. We'll go with that.
Correct. Yeah, actually, it's an excellent question. My response to that particular one would be that the old adage of garbage in, garbage out, right? And hopefully, through the evolution of the process, as you go from one model to another, that particular model, as it's being refined, a lot of those particular concepts are being reevaluated every time they come through, and they're therefore being better refined and better understood, and then applying to those particular ones that we have. So therefore, as you go through the evolution from one model to another model, they just end up getting better and better as you go along. Yes, there is definitely a substantial investment in time when you first start off building the particular model. But if you start off with a good groundwork for those particular parts, it just makes the transition a little bit smoother. One of the things that is also touted about MBSE is that it allows that particular feedback to come through. So therefore, if you do start off with a bad model, through the process of things being reused, hopefully that it will end up being will get corrected as you go along, and therefore improves the model in the future. I hope that answers your question.
Absolutely. Thanks so much. Any other questions?